topic of this meetup is functional reactive programming, and I'd like to ask the audience who is familiar with FRP to some extent, and who doesn't come from a functional programming background. Okay, so you are actually in the minority. That's good to see. Well, my presentation is really just a really fluffy, high-level introduction, and the other two guys will give you some more practical demos. So I just sort of try to provide some context for what they are going to say. So let's see, functional reactive programming, so many buzzwords. What does it mean? Let's start from the words. It's not going to be long, don't worry. Everybody probably has some vague idea what functional programming means. I'll just try to sort of recap what I think the essence of it is. And the essence is really referential transparency, which really just means that you can take any expression and extract it into a definition, or take any definition and inline it, and that doesn't change the behavior of the program, and sometimes it doesn't change the meaning of the program, and sometimes not even the runtime behavior. Of course, this is a prerequisite of basically freedom of side effects. If you have side effects in your functions, then this property obviously doesn't hold. And in order to turn smaller subprograms into bigger programs, we use functions as a primary means of composition. And then we have some nice consequences of this paradigm. For instance, we can do some equational reasoning, we can do some kind of compile time analysis that we couldn't do when we have side effects. Reactive is a bit of a, well, bastard child as a term, because nowadays it's more like a buzzword. But the thing is that the term reactive was first introduced, well, in the late 80s or mid 80s, and reactive programming simply meant programs that were embedded in some environment and that their speed was determined by the environment. This is in contrast with interactive programs, which themselves control the speed of the interaction. So I guess nowadays we would be calling these real-time systems, either hard or soft real-time systems, like for instance embedded systems or video games are two very prominent application areas. But to reflect to the confusion with the terminology, the thing is, if you say look up reactive programming on Wikipedia, the first thing you will see is data flow networks, event propagation, and so on and on. And the thing is, when you put reactive and functional together, then indeed I would say that kind of holds. We are going to be thinking of data flow and data dependencies and whatnot. But in general, reactive programming as the original term is sort of a more broad term. So what is FRP as it was conceived in the mid-90s? It is really the background of everything that we're going to be seeing. It's actually a very simple idea. Imagine that you have some module, some entity, whatever, that an object, which has some internal state, and over time the state evolves, changes, and then this program emits something. And because we are doing functional programming, there are no side effects, which means that the output of a program perfectly represents the program itself. So let's say that we take the whole output over the lifetime of this entity or program and say that this is just a value. And if we look at the whole lifetime as a time-varying quantity, as just a value, we get some really interesting ways of composing programs. And this is basically the core idea. So the original formulation distinguishes between two different kinds of entities. Mostly the difference is in the time-wise behavior. And, well, there are two names, behavior and event. And what I wrote here was actually a kind of measly attempt of defining some denotational semantics, but it's really just hand-waving. But what I wrote basically means that behavior of alpha is a type, we can think of it as a type with a parameter alpha, can stand for anything, int, bool, something more complex. So behaviors are basically time-varying entities that are available at any point of time. So if you want to form a mental model of behaviors, you can think of them as functions from time to alpha. So you just plug in any time, you basically look at the whole lifetime of your evolving system from a distance. So you plug in any time, and then a behavior tells you what value it yielded at that time. And then a kind of dual of behavior is event, also a generic type. An event is essentially a kind of time-varying quantity that is not present at any time, only at certain discrete points of time. So, for instance, one mental model that you can assign to it is a stream of time-stamped values. And just to give you two more concrete examples, we can say that, for instance, a microphone can be considered as a behavior of type float. So it's just a stream of floating point values. Or a keyboard is an event of key codes, whatever key codes are in our system. So keyboard doesn't give us a continuous input, only some occasional occurrences. So let's look at two very simple examples. Again, these are conceptual examples, not necessarily implementations. So let's imagine that we're writing a very simple program where we, say, show a ball in a window, and we want a behavior where we click somewhere in the window, then the ball automatically teleports there. So in order to describe the behavior of the ball, that is the behavior that carries the actual position of the ball at any time, we can say that if we have a behavior for mouse positions and an event for mouse clicks, which basically tells us when the mouse clicks actually happened, we can, for instance, use some kind of built-in primitive called snapshot, which takes an event, takes a behavior, and yields an event which has the occurrences at the exact same times as the original event, but the values are replaced by the samplings of the behavior at those times. And then we have another built-in, a very typical combinator in FRP systems, hold, which basically just formally converts an event into a behavior. So basically it gives us a behavior that always yields the last value that the event gave us. And we can also take this program and actually draw it if we want. And in this drawing I can distinguish between behaviors and events by showing events with dashed lines, sort of showing that they are not always there. So snapshot takes a behavior and event and yields an event, and then hold takes this event and turns it into a continuous behavior, and that behavior tells us at any moment where the ball is. And if you try to write the types of these built-ins, you can see that they can also be defined in a generic way. So snapshot takes a behavior of alphas and an event of betas, and it just throws away the betas and basically replaces them with whatever the behavior carried at those points. So it returns an event of alphas. And hold similarly converts an event of alphas into a behavior of alphas. So it, of course, retains the type of the values carried by these reactive values. Another very small example, again, is another kind of logic for the ball position, where we are moving around the mouse over the window, and the ball follows our mouse as if it was connected to it by a spring. So spring motion is very simple to define. You get it by taking the vector that points from our current position to our resting point and then multiply it by a spring constant. This gives you the acceleration. So in order to get the position from the acceleration, we integrate it twice. And let's assume that we have an FRP primitive called integral. And some FRP systems actually do have similar primitives. And the funny thing is, here is that the definition is recursive. Like the ball position is defined in terms of itself. And again, if we were to make a drawing of this, we can see that the recursion really just translates into a feedback loop in a data flow view. Now, whether an FRP implementation allows you this kind of recursion, that's another question. In most cases, you have to introduce some kind of explicit delay in a feedback loop. Otherwise, of course, the results are not well defined. But for instance, you can kind of define a system which works with integrals. And of course, constants are just a special case of behaviors, which are always the same. But we could say that let's actually make that constant depend, say, on the microphone input. So if we are shouting in the microphone, then the spring becomes much stronger. And well, the nice thing is that these stateful things and various kinds of inputs and outputs are really easy to combine. But now comes a really, really hand-wavy section where we kind of try to motivate this whole idea. And by motivate, we can list a few desirable properties that are a consequence of using this paradigm, but not necessarily exclusive, of course. So one thing we get is a very lightweight way of defining stateful entities without, say, having to introduce new variables or having to pollute the state space of the program otherwise. Like, for instance, in an object-oriented language, if you need extra state, you need to somewhere introduce, say, a new field in an object, or even define a new object because you don't have the right types defined for you. And in many cases, for us, say we just have a simple function application, at least formally a function application, but this somehow magically gives us all the extra state we need. And we get something similar with languages that have, for instance, support for a yield construct. So, say, for instance, C# enumerators. If you think of them, you can define, again, a stateful processor in a way that the state is encapsulated in local variables of that definition, which is nice. But the fun thing about FRP is that you get the same thing without any kind of special language support for it. So FRP systems, for instance, can be defined in Haskell without any kind of runtime support. Another thing is, of course, complex event handling. Like, everybody loves their callback hells. And in this case, you can see that with this kind of composing programs, you don't have to fracture your logic, like especially event handling logic, into separate functions. Not as much as with a traditional callback-based method. So you really more directly define the data flow that you want. And you can more directly see the timely behavior of your program. Say, if there's a delay somewhere, you have to explicitly add it. So again, just being more concise and keeping the things that belong together really physically together. And then one consequence of really respecting the property of referential transparency is that our system is going to be transactional. So basically, the event propagation has to be atomic if we are to respect referential transparency. We cannot observe an FRP system state in an inconsistent state, like at the moment when it is still inconsistent, when we're still halfway propagating. The results don't depend on the order of the events firing. They are always well defined and defined explicitly by the programmer. And then again, because we're doing functional programming, there's really nothing implicit happening, like there are no side effects. So anytime we want to mutate the state, we have to exactly describe what was the starting point and what the ending point has to be, how it is derived from the starting point. No surprises. And an interesting thing about functional programming is that you have to basically write everything that affects the outcome of an expression or the final value of an expression in the definition of that expression. And functional reactive programming inherits this, taking it to the next level. That is, if you have a piece of program, you will actually have to mention every dependency it has in a very rigorous way. There's no such thing as you, say, defining an interface publicly that would allow anyone else to mutate your internal state. It's the other way around. You basically define the logic of reconciling all those outside right attempts explicitly. There are no shortcuts. If you don't know all your dependencies, then you will have to define some kind of explicit extension points, but still you will have to tell how you handle whatever input comes through those extension points. And another interesting bit is testability. Since now time-varying quantities are just values, we can, for instance, write quick check style tests for behavior over time, which is a really handy thing. Like, you can define your invariance in terms of some kind of verification function that returns true or false depending on whether your output matches certain criteria, and you can take it to the next level by, say, using quick check or some other similar tool to drive your pure logic. So what is the design space for FRP systems? There are really two main aspects of it, and they are not going to be very surprising. First of all, we have choices for what the main building blocks are like, and we have also choices about the means of combining them. No surprises here so far. For building blocks, there are really two main approaches that you will encounter. The first is basically what I described as the core idea, that we have events and behaviors, maybe named differently, but that's the basic idea. Let's refer to these guys as reactive values in general. So making them the first class elements is one way of approaching building FRP systems. And the other approach is taking the transformations between these values as the basic building blocks. So if you think back to the drawing of the data flow network, then the transformers are actually the boxes. But in the original formulation, we weren't really focusing on the boxes, we were focusing on the wires, in a sense. And you can wage holy wars about these decisions, but the thing is that this decision doesn't affect expressiveness. It mostly affects, well, the suitability of your solution in certain application areas. Let me expand. So let's just say value-oriented when we are taking events and behaviors as our main abstraction. So we have event and behavior as types in our system explicitly, and we have functions that take these reactive values and combine them into new reactive values that represent a bigger program that contains the logic for the arguments of those functions. And I would say that when you have a textual language, and this is a more natural way of describing problems, because then your data flow connections are essentially variable references. If you want to get some stream out to several places, you just pass it as a variable, and then it appears in a scope. You can nest your scopes as usual with just about any language you can think of, and simply refer to those variables, and you have a connection in your data flow graph. And the other, the transformer-oriented approach, says that we don't have, or don't necessarily have, types that represent events and behaviors themselves, but we have a type, say called trans, which has two type variables. Alpha would be, say, the type of the input consumed by this processing unit, and beta is the type of the values that it emits. So these would be our building blocks. How do we combine them? Well, we have functions that take these transformers and create new transformers out of them. Like the two most basic combinators would be serial combination, which means that we take a transformer and pipe its output into the input of another transformer, and this way we yield a transformer whose types match the end types, of course. or parallel composition, in which case we take two independent transformers, and when composing them in a parallel manner, we get a transformer with two inputs and two outputs. But internally, of course, those two inputs and two outputs are not really going to coincide in any way. And I would say that if you are designing a visual language, then this is probably a more suitable formulation for it if you want to define clear semantics for it, for instance. And I have to mention that if you read around, then you will encounter the notion of arrows, mostly in a Haskell context. And really, Haskell arrows are basically a family of abstractions, let's say that very nicely fit this concept. So Haskell basically gives you syntax sugar that allows you to embed a kind of visual graph description language, like graph with dot files, which basically just tells you which the boxes are and which is connected to which. And internally it compiles it down to some combinations of these functions. Because honestly, in practice, using these functions directly is not really humanly possible. Like, it doesn't scale. In order to, say, wire a new value into a new place, you have to completely reorganize the combinations. But if you have some visual front-end language that generates it, then it's perfectly fine. And then the other half of the story is the structure. Like, how do we combine our building blocks, be it values or transformers of values? Actually, this is very simple. We have a spectrum. The spectrum goes from static to dynamic. So on the static end of the spectrum, we have systems that can be analyzed at great depth. We can optimize them at compile time. We can run all kinds of interesting analysis, say liveliness analysis on them. But, of course, like, static means that the data flow doesn't change its shape during runtime. But of course it limits us quite a lot, since there are many programs that cannot be expressed in this manner. And the other end of the spectrum is dynamic data flow, which means that you get a lot of extra expressiveness, but you lose the ability of performing lots of different analysis, and possibly you might lose the ability to execute it very efficiently. And then there's also a possibility of having some kind of hybrid solution. Say, for instance, Yampa, if you look around, is one of the possible solutions in this space, which I would call hybrid, where some kind of dynamism is allowed, but it's all predetermined. It's not arbitrary. For instance, you can have some built-in combinator that allows you to have a homogeneous collection of values that you can add to and remove from, but not any kind of structural change. So what does it look like? Like, how do we add dynamism? What kind of combinators do we need? I'll just give you two short examples, but the gist of it is that they need to be somehow higher order. So if we have a value-oriented approach, we might have a combinator, something like switch. It's an event that gives us a behavior occasionally, and if we apply switch to this event, then we get a behavior that itself changes its internal structure. So whenever we get a new event, it means that from now on we will execute the program that the event gave us. And then we continue this ad infinitum. And an analog with the transformer-oriented approach would be something called switcher. And the interesting part is that if you look at this, there's no arrow in this type. This is not a function. Like, this itself is just a transformer, a very generic one, that has two inputs. It takes a transformer and then takes a stream that the transformer can consume. And what it does, it executes whatever transformer it gets on that input and then pipes its output to its own output. So actually, this switcher, for instance, is sufficient to define arbitrary dynamic graph structure, except for feedback loops, of course, which require recursion. But other than that, this is enough for anything. So if you want to define your own FRP systems, then I recommend thinking about how you would implement these things, even if you don't necessarily need them. And in general, if you have a certain application area in mind, then it is always recommended to restrict your system as much as possible because of the extra analysis capabilities that you get out of it. Okay, let's recap just very, very shortly. You can think of FRP as just another way of organizing state, talking about state management. And it's a very explicit way of doing so. And I may say a very pure way of doing so if we really take the functional part seriously. And there is no real true way of doing it. Like, there are so many design choices, and it really depends on your application area, which one would suit you best. And the thing is that this is a kind of big idea, and you don't necessarily have to apply it everywhere. You can really apply it in the large, say, in a high-level orchestration manner where you have some little dirty applications and you want to at least make sure that when they try to cooperate, that makes a bit more sense on a higher level. But you can also go in the other extreme. You might want to define a small component in, say, a very static FRP language and get all the benefits out of it. And of course, you can also just think about these things and let them inform your design decisions. And it's really a big question whether it's worth it to really do pervasively. The thing is that there are no real examples of large-scale FRP systems out there. And it's actually a very interesting question what designing software in an FRP manner really looks like. And my recommendation is just to try to think about it, implement your own system, and try to play with it. Because if nothing else, you learn a lot out of it. Well, that was it for me. And I'm taking questions if there are some. Thank you. Yes?
Scratching the surface with this question, I would guess this is a discussion topic later on this evening as well. But you, considering creating bigger systems in FRP, I think concurrency would be one thing that, or parallelism, that would be required for systems to actually work efficiently. Do you have any insight on how that is done in existing FRP systems? I think many of them are single-threaded.
They are mostly single-threaded, yes. There's nothing really stopping you from doing it, but of course you basically have to do all the consistency management yourself. So if you want to do such a thing, you have to define your own runtime. But I don't think there are any real deep thoughts into it. You just have to define the primitives that you want to support and then do it. But I haven't actually seen anything that would really concentrate on multi-threading. Well, if nobody else is brave enough, then thank you.
I have one question about this. So what's the largest sort of FRP system that you are aware of? I mean, like the application. So because that was your last point.
Hard to say. I know that there are some financial institutions that play around with these systems, but of course we cannot really know anything about what they do with them. But I just heard rumors, but nothing that would be in any way, elaborated upon, let's say that.
Okay, so how do you measure the complexity of an FRP system? Like in the number of nodes or of the graph, or?
However you wish to. Lines of code, mostly.
Aha, okay, lines of code. I see.
It's pretty much the same thing.
Yeah. So how large are these largest ones nowadays that you can think about?
I have no information on this. I don't know. The largest ones I saw were basically limited to a few pages of code.
Aha. Okay.
Basically toy applications. Yes?
We use it in Passport, not really functional, but reactive extensions, which is reactive programming, and the core is actually very much the same than here. And we have 100 developers.
Yeah.
And there is no problem with threading. That's not the problem. One problem I would say is the composition. When you have so many streams, how do you manage where your streams are and so on? So how you combine those when you have so much code? So that we have some kind of event buses or where are those events flowing? That's kind of one problem, but I would say that threading is not the real problem.
Yeah, not by itself, but RX is, well, very outspokenly not FRP. It's just reactive programming. Basically, solving those problems would add the F to it, in a way. Yes?
Yeah, I was just pointing out that the RX solves the concurrency question by not doing FRP. So
Pretty much.
It's all the problems of where the streams or the events are is related to not having a coherent story of how the state evolves.
Yeah. It's left up to the programmer to solve these problems. Anyone else?
I have one question.
Yeah.
Conal Elliott is kind of very adamant about the fact that behaviors need to be some continuous sort of time assumption. What is your take on that? Is it sort of, are the semantics, the continuous semantics, so important, or could we treat behaviors as like, you know, from discrete time to discrete values and things like that?
He says it's very important. My personal take is that it's not that important. Whenever I tried to use Reactive to write programs, the end result was always that I had some ticker event. And in the end, I was pretty much reduced to using it in a discrete time manner anyway. Like, it gives you some nice sort of mental models. It makes the semantics simpler, but I didn't find that useful in practice.
So, is it that after all the behavior is not that important, and it's just the event stream which is the thing? Or?
Well, you have an analog of continuous time behaviors by basically having some ticker that is always there. There is some connection with linear temporal logic as well, like the always occurring events are kind of like behaviors, and then we have the analogs of events as well, and there's some nice connection between the two, but it would be too long to go into right now.
We could talk about that, actually.
Of course.
Yeah, because at some point I studied LPL. Yeah.
Yeah. Now, if nothing else, then thank you for listening.
Switch.
Thanks again.